So yeah, the topic of my talk is pandas should go extinct, and obviously I feel obligated to clarify that not the fluffy things that live at Adelaide Zoo, but in fact the Python data frames library, right? So I'm just going to jump straight into it with this incredibly vibes-based diagram you can see behind me, which is essentially like the adoption curve that you'll typically, take for like a data frame library, right? So you'll kind of start on the far left of this diagram, relatively small amount of data, you'll use Excel, and then eventually you get to the point when you're sort of like, single digit gigabytes where you graduate to pandas, which is the typical path you kind of follow, right? And you'll use pandas for a while, and you'll finish up somewhere in the sort of double digit gigabytes, and you just don't have enough RAM left. Your computer only has a single core, and pandas, or your computer only uses a single core with pandas, and then you kind of hit this cliff, right? And this cliff kind of lives here. And on the far right-hand side, you can see all these lovely Spark derivatives, distributed querying systems, Dask at the top, just to make things a bit more interesting. And you're kind of forced to jump onto these systems in order to keep querying your data, doing analysis, that kind of stuff. Now, my controversial take here is essentially that you can avoid these systems, but probably because your data will never get to that size by using the tools that I've kind of got on the top of this slide, right? So that'd be your DuckDB, which is an in-memory analytics database, like kind of SQL Lite for analytics, if you will, and then Polars, which is a Rust-based data frame library that kind of feels very similar to Pandas, but makes some important changes, right? So, and I'll say this gap kind of happens around the 100 gigabyte size, a bit bigger than that maybe, right? And so the question you might be asking is like, why do I actually care about data sets that are about this size, right? And fundamentally, the answer to that question is, who actually has big data? So this table is taken from a paper published by Amazon themselves. They operate Redshift. Redshift is an analytics database, basically a distributed analytics database, kind of like Snowflake or Spark or whatever, right? And what the table here shows is actually fleet statistics for how many rows are in each table on Redshift, right? And you'll see that 95% of their tables contain less than 10 to the 8 rows. So if we make an assumption and say there's 1 kilobyte per row, 95% of tables contain less than 100 gigs of data, right? But you can make the argument, oh, I have heaps and heaps of tables and I query them all the time, right? You don't. So this is from the same fleet statistics, but actually on query runtime. Now, 87% of queries are concluding in less than a second. Let's make some more assumptions. You have 10 nodes in your cluster. They do nothing but suck data out of S3, and they can each do it at 8 gigs a second. That is a total of 80 gigabytes. In your 87% of queries use less than 80 gigabytes of data. Almost no one queries or stores big data. Well, yeah, almost no one, right? I work for a company that does, but we'll ignore them for now. So I've kind of made the case that no one really has this data, but like you're kind of like, well, what do these libraries look like? How do they work? Shut up and show me the code, right? So the kind of motivating example we're going to use for this is the 1 billion row challenge. Some of you might be familiar. It's essentially a challenge that ran about a year ago to find the fastest JVM implementation of a program that could compute the min, max, and mean for a set of weather station data. Basically, you take the blue stuff at the top and you convert it to the red stuff at the bottom, right? The fastest JVM implementation ran in about 1.5 seconds, pretty respectable. We're going to rerun this challenge with our own experimental setup with a 16 gig CSV, 32 cores with 128 gigs of RAM on an AWS box that I rented. We're going to do 30 repetitions for each trial, and we're going to do two warm-up runs to make sure the caches are cleared and all that kind of stuff. Notably, my examples don't care about output serialization, which the original challenge did. The reason for that is it's just not super relevant to the kind of things we do with these tools. So the first example here is probably something many of you will be familiar with. It's basic vanilla pandas. You read a CSV, you group it by, you do an aggregation, and then we're rounding it, which was the original spec of the challenge. Fine. The one thing I'll kind of call out here particularly is that like Pandas is executing each of these lines sequentially, right? It's reading the CSV, it's doing the group by, it's doing the ag. And the reason that I'm stressing that point will become clear in a second, right? This is the next one. So this is Polars. This is the Rust-based library. It should look very, very familiar to anyone who's used Pandas, with a single exception that group by has an underscore in it as God intended. So you read the CSV in, you do the group by, you do the ag, you do some sorting, whatever. And the last line is the one I'm really interested in here, which is collect, right? So by default, Polars is actually lazy evaluated. It makes a big deal in terms of performance gains because 40, 50 years of database research and optimization actually can now be leveraged by this. As opposed to dumbly going, I'm going to read it, I'm going to group it, I'm going to ag it. It actually goes, OK, here's a whole set of operations. Now let's decompose them into a DAG of operations and apply them in an optimal manner, right? So that's what this collection does. So you get like stuff like predicate pushdown and other real benefits you get from a true full-fat SQL database right here, just in Python, right? And the last part of that, which is new streaming equals true, is actually just enabling it in streaming mode, right? It's like saying, load the data chunk-wise, do the processing, and then spit out the result again, right? Don't store everything in memory in the same way that Pandas does. Cool. And the last example here is DuckDB, which is a bit more wacky, but essentially, as I said, in-memory SQL. So essentially, this should look very familiar to anyone who's done any kind of rudimentary SQL, but essentially you're just creating a table, selecting the things you want, doing a group by, right? Now we get to the interesting part, which are the results. So this table has a few columns. So there's obviously the library on the left-hand side, median duration across the 30 trials, median max CPU, which is basically like 100% is a single CPU core, median max USS. You can think about that as the amount of RAM at max that it used if you killed the process and what you would get back for the operating system. And then swap is in the right-hand column, which is not super relevant for this trial, but you'll see in the future that it is. So Pandas did it in 4.5 minutes. Would anyone like to tell me or guess how fast Polars did it in? Anyone? No.
1 second.
You're not far off. 5 seconds, right? So that's within an order of magnitude of the best hand tool to JVM solution running native code, right? It used all 32 cores of your machine that you actually paid for, as opposed to the one with Pandas. It used 18 gig of memory, which is reasonable. And again, it didn't dip into swap because the machine has so much memory it doesn't need to. And the last one is DuckDB. So DuckDB did it in 5 seconds, used full 32 cores, and did it in 2 gigs of memory. Not bad. Now, the question you're asking now is like, this is wonderful, this is really good empirical production performance, great, but like, how does this actually change my life day to day other than when the jobs run? And so the really way to think about this is like, does this speed up your dev loop, make your life better, that kind of thing, right? And so the next set of trials is we just did the same test again, but on my local laptop that has, 16 gigs of RAM and 8 cores, right? And here's the results. So Pandas did abysmally. It swapped out heaps of stuff to RAM, and it took ages, and it used a single core again. Polars obviously did respectively again, used all 8 cores, very, very slightly dipped into swap. And then DuckDB obviously was the real winner here with 500 megs of RAM usage, all 8 cores, and ran in pretty respectable time, right? So I guess, yeah, the message here is like, it improves your dev loop, it improves your production performance, right? And much more efficient with resources. So what do these tools really give us? Great performance on a flawed benchmark. All benchmarks are flawed. This one is particularly flawed because I basically chose it to demonstrate some of the benefits of using these other tools as opposed to Pandas, right? So one of the main ones would be painless multi-threading. I didn't do anything with a thread pool. I didn't create things. I didn't worry about fork join. I just got all of the performance out of my machine, right? Streaming, which both of these tools use under the hood. DuckDB does a lot of that predicate push down streaming stuff as well as Polars, which just filter things through memory essentially, right? The other thing is spill to disk, which is not obvious in this example, but essentially Pandas swapped out to disk, which is fine because that's what the operating system is doing, but the operating system has no idea what your job is doing, right? These frameworks actually have the ability, or tools have the ability to spill to disk natively, so for large computations they can say, I don't think you're going to need this in 10 lines time, I'm going to spill it out to disk, and I'm going to keep the stuff that's on the hot path in memory. That is a big boon. And the last one is really the killer, is lazy evaluation. You can actually create a DAG of the tasks that you're evaluating, and it's going to just execute them in the optimal order, right? You're interested, but shiny tools have hurt you before. We've all been there. Anyone remember Redux? No? Well, I'm not the youngest here then. Cool. So the way you actually adopt these tools is using Apache Arrow, right? This is kind of the de facto in-memory data layout format that the community is kind of settling towards, right? So it's been supported in Pandas since its 2.0 release in April 2023, and support is, yeah, it's getting there. It's really getting there. But I guess the key detail here is both of these tools, Polars and DuckDB, support memory, zero copy serialization between representations. I can go from Pandas to DuckDB to Polars to back again without copying anything in memory if it's all PyArrow backed, right? If the Pandas data frame is not PyArrow backed, you get a fresh copy, but as we've already seen, these tools have much lower memory footprints, and so having a duplicate copy in memory is probably fine if you can afford the Pandas overhead in the first place. So let's look at another practical example, the New York taxi data set. So it's a data set of every taxi trip taken in New York between 2009 to present, right? With the data is on sort of monthly files, and so you can sort of process through them. Corporate wants to find out if the pandemic made cache less common. So we're looking at the files between 2019 and 2022. This is about 3 gigs of Parquet file on disk. We're using DuckDB with Pandas, but you can actually mix and match these tools as much as you want. You could use Polars and Pandas, or every combination thereof. So there's kind of 4 functions that I'm going to call out here. Don't try and read all this code. There's just too much of it going on. But there's essentially 4 functions here, one for reading and computing for each of the particular libraries. And what you can see is we're going to mix and match them around and show how you can just use them together. So the key points on this slide that I want you to take away is reading this data from Pandas is you can naively just do a loop and just merge them all together in memory. And basically, we're just doing this D-type backend PyArrow. At the bottom of the slide, there's a bunch of boring data sciencey stuff where we have to clamp the data to the right range of all that nasty stuff you have to do when you actually use real data. So the Pandas compute also looks really, really familiar to us. We're doing a group by, we're doing an ag, we're doing some horrible unstacking stuff in the middle, resetting some indices, and basically summing up all the column levels for the enum for cash payment versus card versus whatever, right? Again, don't sweat the details too much. These are kind of here for completeness. DuckDB looks very familiar again. This is just a select statement in SQL. The thing I really want to call out here, though, is this line, which is really sick. Because essentially, DuckDB is just merging these files for you. It's using a glob pattern to just like find all the Parquet files in this directory and just go put them together, right? The last part I want to call out here as well is this stuff, the kind of boring data science-y miscellaneous stuff I was talking about before is actually happening at the point where you read the data in. So all this stuff about predicate push down and like, filtering data that you don't need is happening for you, right? So Pandas had to read all that stuff in, and then you had to say, ugh, chuck away the bits I don't want, whereas this is like, just don't read in the crap that I don't want in the first place. So that'll help you save a lot of memory. The DuckDB computation, this slide really is concluded for completeness. I wouldn't try and grok all of this. It's a bunch of common table expressions put together with some joins and smushed together. I wouldn't stress about the details. You can look at this later. The last part here, again, I'm not going to enumerate fully, but essentially is just like, it is all of the combinations of these things, right? It's reading and writing with each framework together and then using pure solutions for each of them, right? Again, wouldn't stress, it's just there for completeness. The part we're all really here is for the performance on my actual machine sitting at home on my laptop. So pure Pandas is obviously the worst. We all knew that. It used about a core, it used 14 gigs of memory and swapped out lots of stuff. DuckDB doing a reading and Pandas doing the thinking kind of gets your runtime down simply because DuckDB can read this stuff in parallel. It can take those glob patterns and just go, I've got 8 cores, I'm going to use them and just read as much as I can. You use all 8 cores. You still swapped out, probably because the Pandas group by essentially expanded and then contracted in memory again. And then if you see the example where the Pandas does the reading, you still get the benefit, but you don't get this expand, contract pattern in memory because it's not being done by Pandas. And finally, the pure DuckDB solution, 8 cores, 200 megs of RAM versus like 15 gigs for all the other ones. I'm impressed. Cool. Did cache usage fall over the pandemic? Yes. I don't know if it's actually scientific. I don't really care. Here's a chart just to prove that I did the actual research. For some reason, in March 2020, people started using cache more, which I don't understand or believe. But that is the chart. It did go down. OK, so you're technologists. You should be skeptical. If you're not, become skeptical. Why shouldn't you actually just listen to me, right? The answer is, I'm just a dude with a laptop. Do your own research. Clone my code. It's open source. It's on GitHub. Do your own benchmarks. Figure out how your own workloads work. Don't just take as rote the thing that a dude on the stage with a sweater said. The second part is you're super deeply integrated into the Pandas ecosystem, right? I did my honors degree in energy research, which used there was this weird package that did energy modeling that used Pandas as like a base data structure, which is really cooked in hindsight. But those people who are doing that kind of modeling are not getting away from Pandas, and honestly, they probably shouldn't. Another example is kind of like geospatial as well. Don't bother, it's not really worth it. The last point being, let Pandas cook, right? Let them improve, let them get better. They are the kings, right? And that's true. They have made progress on integrating PyArrow and getting better, but that progress has been honestly abysmally slow. And the other part I will say is that, there are benefits to switching off of Pandas that go beyond performance. There is a lot of stuff around ergonomics and API grokability. The mental load of using Pandas is significantly higher than just writing SQL, in my opinion. And the other one is a transferable skill set. One of my major criticisms of data science as a field when I started out was that it basically just feels like you're just learning an API. There's no novelty there. It's just how do I glue together these Pandas things, right? And what you actually get by switching to a tool that allows you to use SQL, for example, is transferable skills across different domains. I've suggested 2 tools. Which one is better? This really, really depends on your preference, SQL versus code. I personally prefer Polars because I like composable functions, I like unit testing, I like that kind of stuff. But DuckDB goes well beyond performance, right? You get local first analytics. You could do local first analytics on an embedded Android app, right? Say you're making a health app, you just embed this binary in your code, and you can do cool analytics dashboards for your users without sending anything to the server. That's nuts. The other one is compile it to WASM and just do SQL queries for visualization from the front end. Your backend doesn't return JSON data. It returns signed S3 URLs, and you can just query them. That is nuts. It is so cool as a more app devy kind of person as opposed to data person. So that kind of brings us to the takeaways of this talk, which is basically you can't avoid complex distributed querying systems, but you can defer them potentially indefinitely by just not using Pandas in the first place. And the second one is we really are experiencing a renaissance in Python tooling at the moment, particularly in the dataframe space. Actually get out there and try some of them. Your assumptions are no longer valid from 5 years ago. And finally, just a bit of shameless self-promotion. Code for this is on GitHub. I have a LinkedIn. I have a blog that I occasionally post to. If you want to follow me on Twitter, don't, because I don't care what you think. I believe I have a slide as well for feedback and what's up next.